Hello, my name is Matt Davis. I'm the Managing Director of QA Systems in the UK. Last year at ATC, we presented automated requirements-based testing for ISO 26262. So this year, we're going beyond automated requirements-based testing to look at the other elements of the testing for the standard. The ISO 26262 software verification phases mirror on the right-hand side of the V model the implementation phases. Those are all covered in parts 6 to 8 of the standard. And then subsections 9 covering software unit verification, 10 software integration and verification, and 11 the testing of the embedded software. All of these are detailed in part 6, the product development at the software level. In this presentation, we are going to concentrate on achieving demonstration that there are no undesired functionality or functional safety properties. This is going beyond the requirements, specifications and testing that ensure that the safety measures are properly implemented and that they comply with the architectural or unit level design. So looking beyond requirements-based tests and no undesired functionality or functional safety properties, we can consider a verification order. The first thing we look to do is some form of static analysis to see that the code we are writing meets the quality standard. In most cases, this will be MISRA compliance. After that, you will be looking at does the code do what it should do. This is the functional requirements-based testing and non-functional requirements testing. But beyond that, we have to look at whether the code does not do what it should not do. You may consider this a form of robustness testing. And of course, is the code tested enough? The purpose of structural coverage testing. In this presentation, we will not focus on static analysis, but on the dynamic testing capabilities and how that goes beyond requirements-based tests. So that's really 3 and 4. In Table 7 of ISO 26262 standard, the methods for software unit verification are identified in the table below, and whether they are applicable or required or highly recommended by different ASILs of the standard. The first section we're going to look at is control flow analysis and data flow analysis, 1F and 1G. Zooming in on those, we can see the guidance in addition to the table. It's clear here that the methods 1F and 1G for control flow analysis and data flow analysis can be part of the methods 1E, formal verification, 1H or 1I, static code analysis and static analysis based on abstract interpretation. The guidance is clear that the latter can be used for control flow graph generation and data flow analysis. So, flow analysis can be undertaken by static analysis. In terms of Table 10, the methods for verification of software integration, there is also the verification of control and data flow. Again, variations of recommendations by ASIL. Annex D, the informative part of the standard, provides examples of possible mechanisms that can be considered for the prevention or detection and mitigation of the listed faults. You can see highlighted in red the results of static and semantic code analysis for control and data flow analysis can provide the evidence demonstrating freedom from interference. Similarly, for both memory and exchange of information, the approach is applicable. So again, flow verification can be undertaken by static analysis. This somewhat differs in approach from some of the other safety critical standards, such as the avionics standard, where control flow and data flow analysis must be done during dynamic testing. However, within the ISO 262 standard, verification of the control flow can be undertaken dynamically during the unit and integration test phases. The scope for the analysis is function calls, where the controlling parameter or pointer is fixed or dynamic. The verification techniques cover three main elements. Where controlling parameters are constant or set at compile time, code coverage of calls is usually sufficient. But the structural coverage alone, where parameters are controlling paths through the code dynamically, is not enough. Here, structural coverage analysis is also required for dynamic function pointers where the value has been or has not been initialized before use, and where it is has all possible values. So in other words, code coverage measuring the function calls executed from all possible calling points is necessary, statically or dynamic. In addition to that, verifying calls and checks on modifications made by the controlling functions prior to controlled call executing are possible where the test framework allows. Call sequence verification in tests is particularly important here. The order of calls being made is part of the dynamic flow verification. Checks on what is passed over those calls in terms of the parameters and pointers modified before execution of a controlled function also permit the verification of control flow. For the dynamic verification of data flow, the scope is slightly different. It's about data. The scope is all control paths influenced by data outside the function. That may be file static data or global data. The dynamic verification techniques here again include code coverage of all control paths through the code, which may be influenced by a fixed parameter value or global data are executed. The code coverage exercised for all equivalence classes of potential states and legal transitions of such states can also be undertaken using user context coverage. The equivalence classes of these potential states and legal transitions is only measurable if you also understand the context or the transition being made. And of course, checks on the reads and writes of data occurring during unit and integration testing also allow the dynamic verification of data flow. Beyond control and data flow analysis, there are other dynamic testing methods in tables 7 for unit verification and 10 for integration. These three principal techniques are interface testing, fault injection testing, and resource usage evaluation. I'm not going to touch on back-to-back comparison between model and code. That is only applicable if you are doing model-based testing and code generation from it. There's a whole separate presentation. We may get to that one next year. So for interface tests, the purpose here is to demonstrate the integrity of used and exchanged data over such interfaces. What techniques could be applied? The first, of course, is to control the interface so that you can either simulate its behavior or intercept its behavior. In the diagram, you can see the options to remove something for simulation or to use it for interception. But there is also a chain of other events or calls that may be made, and in this case we need to look at resolving the link dependencies, especially challenging for C++. So what does control to simulate or intercept mean? Firstly, you need to generate some form of control. A very common way of doing this is to simulate the calls using a dummy. This is simulating the interface to the call, not the entire object that is being called. Common terminology for this is stubs, mocks, fakes, dummies. However, in addition to simulating a function, such as the diagram below function B being called from function A, you also have the option to potentially intercept and use the called object. In this case, you might consider it being wrapped. before and after the behavior. You can also, of course, resolve link dependencies. What do these control functions enable us to do at interface testing? Well, the first thing is they should be programmable for each call so that you can do different things with automated checks and allow different behavior to be verified on each time a call is made, potentially including additional C or C++ code to add or verify further behavior. That verification can include checks on the parameters passed over the interface, or of course on data accessible to the functions, which may be set or checked. In addition to the instances being used and the checks, you may want to be able to control which instances and behaviors of these simulations or interceptions are used in each test case. You would also need to have that done flexibly so that you can have quite complex sequences of calls. Verification of those call sequences should be within each test case and to verify that the correct order and the instances that we used with each call occur within each test case. Drilling down, what does interface simulation mean? A stub, mock, fake or dummy replaces the called object at link time with some dummy code. The dummy code is a replacement of the interface of the object, not its body. What does this mean? It means that the source code is making a call where you can check the parameters and the order to the called object, but instead of it being used, you use a mock or a stub. That mock or a stub allows you to choose and set return values and parameters or raise exceptions. Interface interception is a different concept. Again, it is the function or method with programmable instances, but this time a wrapper intercepts specific calls to and uses the real called object at runtime. It does so by intercepting with a wrapper, wrapping the call. This allows you, in a before part of the wrapper, to do what you can in the stub or mock, checking the parameters and the call order. But it offers another level of control in that you can modify those parameters or set other preconditions prior to the called object executing. This may be seeding data into the called object for the test case, such as a database. It may be resetting a register before the called object is executed in a particular test environment. But the biggest difference between the simulation and the interception is this part. For a simulation, I assume what the called object is going to do and place that into my dummy, stub or mock. With an interception, I use the real called object and therefore I can check what it actually does, not rely on my assumption of what I think it will do. That means I can check the parameters and the return, and also set or check other post conditions, including accessing data, registers, etc. This is the after part of the wrapper. The after part can also modify the parameters received from the called object and return back to the source code, particularly useful for error injection at integration testing. So what are our test options for interface tests? Take this small example of some code. Different units, some data, making calls. The first question is, where do I control? The interface entry point is, where do I start driving my software under test from my test driver scripting? Is that the top level function unit A, or perhaps functions further into the flow of the code, such as unit D? With simulation, I can take a group of code that is not necessarily all integrated. Stubs or mocks can be used for calls to items that are not present and can be simulated by them. Where items are integrated but I wish to control, I may want to use wrappers for specific calls to integrated items. So what do I do with these different interface tests? Well, here are a number of common actions that developers would use to verify the behavior of their interfaces: calling objects, checking the order, setting or checking data, and outputs. With a stub or simulation, of course, I must use the simulated object, but I have somewhat limited capability in what I can do. And of course, I must set a return from the called object if my execution flow will continue, assuming it's a non-void function. With wrapping, it is much more flexible. I only need to link in the wrapped object. However, you can see with the combination of both simulation and interception options for interface testing, we get complete flexibility to control the call interfaces for both isolation unit testing and integration over testing. Turning to fault injection tests. The purpose of fault injection tests is explained in the details behind the table. It is to modify the software unit under test to inject faults and to verify the correctness of hardware-software interfaces in particular at the integration level. The techniques we can employ to achieve these fault integration tests are to control the call interfaces using simulation or interception at the call interface boundary to interject faults. In addition to that, however, we could also use a test driver. The test driving script may inject error inputs when calling the software under test initially. So you have the choice of setting your injection at the very start, in this case, or at a point where a call is made by the software under test. However, some test drivers are capable of offering custom code insertion to inject errors anywhere within the software under specific test conditions. This custom code insertion, usually achieved through instrumentation, allows more fine-grained fault injection, so it could be used before or after any statement within the code, and is considerably more flexible than just making tests with injection at the very start of the calls or during at individual call boundaries. It also avoids using things like conditional compilation to achieve the same approach, using debug jumps, and examples might include changing local variables or resetting hardware registers or even firing interrupts. Resource use evaluation. The purpose here is to verify the processor performance, its minimum or maximum execution times, the storage use, and the bandwidth of communication links. It is most properly used, as the standard identifies, when executed on the actual target environment. The techniques, which can be employed on host in a limited capacity or more fully on embedded targets, are again controlled by the call interface, using simulation or interception at the call interface boundary to verify resource usage, bandwidth, and timing. In a test driver, the use of the driver script can check resource usage and timing during and after execution of the test. We can also use custom code insertion to check resource usage anywhere in the software under specific conditions, in the same way as fault injection. So we have seen some techniques. The methods for deriving the test cases to be used in those techniques are, of course, analysis of requirements for requirements-based testing, but these three others in tables 11 and 8 for integration and unit testing, respectively. The generation and analysis of equivalence classes, the analysis of boundary values, are things we will dive into further because these are recommended or highly recommended for most ASILs. Error guessing based on knowledge or experience is something created in a lessons learned approach and can be something that is used by very experienced testers, but is not very easy to abstract and explain what good lessons might be for general software. So I will concentrate on 1b and 1c. Equivalence classes. So equivalence classes are where variables or parameters have the equivalent, i.e. the same expected effect. Now there are always too many values to test all the possibilities of a variable holding potentially tens of thousands of values. The combinatorial effect of several variables can be extremely large. So possible values are divided into equivalence classes through analysis. The purpose of that is not efficiency, but test completeness, because it allows you to identify what possible equivalence classes there should be and to verify that those are being achieved in your tests. Each equivalence class of values used is used as inputs to tests and potentially throughout tests. Equivalence class analysis, of course, supports both requirements-based tests and the robustness tests. So how may we use this technique? One very obvious way is to use the same test case, expected behavior, with multiple values for the variables or parameters within equivalence classes. This is a belt and braces approach, to use more than just one value for an equivalence class. But it is also easy to modify the expected behavior of tests between equivalence classes if you use looping or parameterized tests. In terms of test framework support, what we should be looking for here are frameworks that base their support for parameterized tests on input variables and parameters using standard data types for code. Also providing options not just so we have to choose and specify each individual value on its own, but using things like ranges and deltas of values too, with data sets that can be imported and exported. For boundary values, where values of variables or parameters are below, at, above, or even out of range values, again, data type boundaries, for example minimums, medians, maximums, can be used. Values where the code uses relational operators, greater than, equal to, etc., are there to determine behavior of the control flow in the code, and therefore are very useful to be tested with boundary values. In addition to values just above, just below, at the maximum and the minimum, etc., you may also use special values, particular characters. For strings, you might use zeros quite frequently, or null values. In addition, invalid data or out-of-range values can be used for boundary value testing. The use of looping and parameterized tests here makes it very easy to have the same test case expected behavior used with all the boundary values that you are testing with. It is easy to create tests with modified expected behavior depending on the boundary value input. For test framework support, we are looking for predefined sets of boundary values for each input variable or parameter. You might consider these rule sets for each data type. Makes the testing process easier. In addition to the different methods and techniques, we also have structural code coverage. Table 9 details the structural coverage metrics at the software unit level, again by ISO A up to D. Modified condition decision coverage being the hardest to achieve and only applicable at level D. Table 12 identifies the structural coverage metrics at the software architectural level. It's appropriate here that the function coverage and call coverage are different from that obtained within the unit level, because you are looking at the interaction of the code, whether functions have been called and returned. So, what are we looking for from structural code coverage to help us achieve ISO 26262 requirements? Firstly, it needs to be an efficient analysis and reporting. The standard, as well as having different requirements for unit and architectural level coverage, specifies these in its metric sets. But there are also considerations for different execution platforms Have I run the tests and executed the code on different target platforms, for example? Or have I got different source build variants using hash defines, which will affect the way the source code is translated into the object code executed on the environment? It's important to look at standalone or integrated code coverage with the test suite. Integrated coverage is needed to avoid a separate manual review activity, where a standalone coverage measures the code being executed no matter what drives it. Whichever way you use it, the data needs to enable diagnostics at every stage and level and run of tests to help optimize and to aggregate. As well as aggregating the results, you also need to drill down and to be able to look and report. Drill down views, filters, reports are very powerful tools for code coverage and to help identify gaps in testing. Some examples on screen. Another capability here that is very useful to have in terms of structural code coverage is if you are measuring the coverage for each individual test case, you can determine which test cases are actually covering the same code as other test cases and therefore may be redundant. Automatic test case coverage optimization identifies redundant test vectors, aiding the selection of different input combinations to drive the software under test. So, a summary. For ISO 26262, we have requirements-based testing. It is and remains the most important verification activity. It's there to ensure functional, non-functional, and safety requirements are satisfied. But it is not enough to comply with the ISO 26262 objective that there is no undesired functionality or functional safety properties. So beyond requirements-based tests, we can look at control and data flow dynamic verification, interface tests, fault injection tests, and resource usage tests. With the equivalence partitioning and boundary value analysis techniques, with a safety net supplementing the whole lot using structural code coverage to make sure we have tested enough. In addition, of course, there is static analysis, not only for the coding standards compliance to MISRA, but also to support control and data flow analysis. It's very common for people doing testing to use tools. The ISO 26262 standard in Part 8 has a section called Supporting Processes, Section 11, Confidence in the Use of Such Tools. Their principal purpose is to demonstrate that the tool is suitable for use. So to be compliant with the standard, the tools you use need to be certified as suitable for use at the appropriate ASIL. Of course, you can do this yourself. You can certify a tool from somebody else or create a tool and write all of the certification evidence for it. But if you are considering purchasing a tool, then you should look to select vendors that can provide this and support your testing to the standard. This particularly involves two elements: tool certification kits and guidance on how to use the tool to meet the requirements of the standard. Again, some examples from my company. So, we're now going to look at an example approach for hardware in the loop testing using fault injection at an interface unit test. This example uses controlling colors of an LED. There are low-level calls to the read-write operations on the LED port. Intercepting those with a return from the LED to modify the call behavior at runtime, hardware in the loop, allows us to inject faulty error conditions back to the controlling function to verify it and to achieve the desired structural code coverage. The techniques we'll use would be wrapping interception interface test to inject the fault and measurement of the code coverage to demonstrate that the hardware error software is achievably testable with hardware in the loop. For this, I'm going to play a short video. It's a video recorded using our Cantata tool, which is an ISO 26262 certified tool, and that video will run now. To learn more about testing for ISO 26262, whether it is automated requirements-based testing or beyond requirements-based testing, please do visit our website, qasystems.cn. Our colleagues at WaterTech will be delighted to help you. Thank you for listening. Do you have any questions?